All right, guys, let's start. Okay. So now we are starting with a new topic, which is called your partial differential equation. Partial differential equation. This is the first chapter. Chapter name is your Introduction to Partial Differential Equation in Quant Finance, also called PDE. And lesson one is about what are PDEs, right? So big picture first, right? Why this lecture matters. A PDE is not useful in finance just because it is an equation. It becomes useful only when you tell it that, let's say our question is, where do we start? The mathematical object here is that initial condition. In financial meaning, it is like you're looking at today's asset price, today's portfolio wealth, today's short rate. Then if your question is what happens at maturity, mathematical object for that is your terminal condition. Financial meaning is option payoff, your known cash flow. If your question is what happens at edges, mathematical object for that is boundary condition. Asset price goes to zero, asset price becomes very large, barrier is hit. If your question is what solution is allowed, mathematical object here is constraints. So financial meaning is no arbitrage condition, early exercise, admissible strategies, etc. So the main idea of this lecture is that PDE gives the rule of the motion. Boundary and initial conditions makes that rule financially meaningful and solvable. Okay. So the first slide introduce the lesson partial differential equation in quantitative finance. A PDE or partial differential equation is an equation involving derivatives with respect to your more than one variable. In finance, the most common variables are like your asset price, time, interest rate, volatility or variance, value of option, derivative, or portfolio, right? For example, an option value is usually written as, option payoff, right? So you generally use stock price, time. Sometimes you use your risk neutral probability also, right? So value depends on your stock and time, right? So that is why PDE matters in quantitative finance. Option prices, bond prices, interest rate, derivatives, portfolio value functions, and risk measures often depend on multiple variables at once. Okay. Now we go to the next part. We'll try to understand why partial differential equation need your boundary and initial conditions, right? So the point here is, right? The point here is that so partial differential equations typically admit infinitely many solutions. Okay. To obtain a unique and meaningful solution, we must impose your appropriate initial conditions, boundary conditions. Initial conditions specify the state of the system at the starting time. Boundary conditions specify behavior at the edge of the domain, which I told you, right? Mathematically, a PDE is the form, this particular form, which is given. So a PDE says, or PDE often kind of admit infinitely many solutions unless we impose conditions. The PDE equation is shown here. What does it mean? It is basically pronounced as your L operator applied to U of x and t equals 0. Here, U, x and comma t is unknown function we want to solve. X is the state variable as asset price, t is the time, L is the differential operators. LU, right, is the rule that the function must satisfy, right? You should think of it as a machine containing derivatives. The PDE alone tells us the general behavior, but it does not tell us the exact financial answer, right? Example, if we, let's say, want to price a financial option, the PDE alone is not enough, right? We also need to know that what is the strike price, etc. That payoff condition pins down the correct option price, right? So financial connection here is that without conditions, no payoff at maturity. The problem is we do not know what the derivative pays. No boundary at s equal to 100. Solver may generate unrealistic option value. No boundary at s tends to infinity. Numerical model may explode. No starting wealth. Portfolio optimization problem is undefined. So the PD is like the engine, but boundary and initial conditions are the roadmap, right? So again, key idea, boundary initial conditions encode real world constraints that make the mathematical problem solvable and relevant, right? not well poised unless supplemented with condition that is still invisible solution. Then we go to the next part. We look at your boundary and initial conditions in finance, and we look at the role in quantitative finance. The slide connects boundary and initial condition directly to your financial markets. For a European call option, the terminal initial condition is given, right? V of S at time capital T equals the maximum of S minus K and 0, right? So that is given. Basic idea here is that if S is greater than K, exercise the call, payoff with S minus K. And if S is less than equal to K, do not exercise, payoff is 0, right? So that is what we need to understand very clearly. Okay. So this terminal condition is given. Idea is take whichever is bigger. This is the option payoff at maturity. In option pricing, this is technically called a terminal condition because it is given at maturity, not at today's time. But when solving the Black-Scholes PDE, we often solve backwards in time from last node to today. That is why some slide may loosely call it an initial condition for the backward solving process also, right? So don't get confused. Basic idea here is that in this particular slide, we are trying to connect your boundary and initial condition directly to your financial contracts. And we are trying to understand that how they are very important when solving financial derivatives or other things, right? So why this all matters? Because let's say financial objective is European option, right? Condition have to be put payoff at maturity. If it is barrier option, you need to have a condition, value and barrier is hit. Portfolio optimization, that is your starting wealth. Interest rate model, initial short rate. Stochastic volatility model, starting volatility. This is a bridge between abstract PDE and actual financial pricing, okay? In quantitative finance, boundary and initial conditions arise naturally from the structure of financial contracts. Initial condition typically represent option payoff and maturity, portfolio value at a given starting time, known terminal cash flows. Boundary condition typically represent behavior option price, asset price tends to 0, asset price tends to infinity, barriers, rebates, or absorbing boundaries. These conditions transform abstract PDEs into concrete financial pricing and risk problems. Okay. Then we get into the next part, which is the meaning of the boundary condition. Boundary condition, when we say the slide introduced the PDE form, right? We can see this is the PDE form. It is pronounced as partial derivative of V with respect to T plus L, operator applied to V equals 0, where partial derivative del Y by del T is how much change as time passes. LV is the effect of asset price, movement, volatility, interest rate, etc. is equal to 0 is the no arbitrage. Pricing balance in the Black-Scholes world, LV, right? This part, right? In this part would contain terms related to delta, gamma, volatility, and interest rate. Boundary condition tells us what happens at the edges of the problem. For option pricing, the domain is usually S kind of 0 to infinity, comma T, 0 to T. Okay, meaning S equal to 0, stock becomes worthless, S tends to infinity, stock becomes extremely large. T equal to T, option reaches maturity, barrier level, knock-in or knock-out event. So the key idea is boundary conditions stop the PDE from producing mathematically possible financially wrong answer, right? That is what we have, right? So boundary condition describes the behavior of the solution at the boundary of the domain of a PDE in finance, spatial domain, asset price S, time domain, it falls within into it. The PDE of the form is this, requires boundary condition to ensure unique and economically meaningful solution. Boundary conditions include payoff at maturity. Behavior S tends to 0, S tends to infinity. Barriers, caps, floors, or regulatory constraints. Okay. Then we get into the next part. We're looking at fixed value versus fixed gradient. This is a very, very important slide, guys, in the world of quant finance, right? The equations are given here, right? The equations are given here, and you have to be able to understand and interpret those equations. So first one is Dirichlet boundary condition, fixed value. The formula is given to you. V of x and t equals g of x and t. We directly fix the value of the function at the boundary. The financial example is V of s and t equal to max of s minus k comma 0. This fixes the value at maturity. So Dirichlet means at this boundary, the value itself is known. For example, right, boundary when European column maturity, Dirichlet is equal to your S comma D max X minus comma 0, right? Boundary condition call when S equal to 0, V 0 comma T is equal to 0, knockout barrier, V B comma T is equal to 0, rebate barrier, V B comma T is equal to rebate. So that's what we have. Most common boundary condition in option pricing represent the payoff at expiration. Then we have Neumann, right? Boundary condition. This specifies the derivative of the boundary. We have your partial derivative of b with respect to x evaluated at x and t equals h of x and t. We fix the slope or sensitivity of the function at the boundary. In finance, slope means often delta if x equal to s. Then we have partial derivative of b divided by partial derivative of s. There's option delta for a deep in the money call when s tends to infinity. The call behaves almost like a stock. So partial derivative of b divided by partial derivative of s is equal to 1. Okay, that's why we say control density delta at the boundary. When stock becomes very large, the calls delta approaches 1. So Dirichlet and Neumann equations, right? Boundary condition. Dirichlet, what is fixed in Dirichlet is the value. The financial intuition is often payoff or barrier value. In Neumann, what is fixed is the gradient slope. The financial intuition is delta sensitivity, delta of the sensitivity of the limiting behavior, right? So that's what we need to understand. Using interest rate and term structure models, an example, limiting behavior often delta resistance to infinity. Then we have Robin, your mixed boundary condition, all right? So again, the Robin condition combines value and gradient, right? The a linear combination of the function and derivative. So pronounced as your alpha times b of x and t plus beta times partial derivative of b with respect to s equals gamma of x and t. Here symbols are alpha beta. Alpha is weight on value, beta is weight on slope, sensitivity. Then we have your gamma x comma t known function v is equal to value, and your partial derivative of v divided by partial derivative of x, gradient sensitivity. Normal condition is useful when neither pure value nor pure delta condition is enough. The financial intuition is, suppose the product has a boundary where the value is partly constrained. The sensitivity in the boundary also matter. The normal conditions are more flexible, right? The example from the slide which are given is exotic options, right? Use cases, exotic option. Why Robin kind of helps Robin boundary condition? Because boundary may involve payoff plus sensitivity. Transaction cost model, hedging costs depends on value and gradient. Partial absorption, rebate model, boundary does not simply give the option fully. This model, boundary behavior may depend on exposure sensitivity, right? So Robin condition says that the boundary I do not care, I do not just care about the value, I also care about how fast the value is changing, right? So appears in exotic condition options, risk model with transaction costs, PDEs with partial absorption or rebates, right? Open condition provide flexibility for modeling risky boundaries when neither pure value nor pure gradient constraints are sufficient. Then we get into the next part, which is your role of your initial condition in the time-dependent PDEs. Right, the slide gives you an equation u x comma 0 is equal to fx, announced as u of x at time equals f of x, right? Meaning at the initial time the function is already known. In finance, this will mean model is stock price model S0 is equal to S naught. Portfolio wealth model W0 is equal to W naught. Interest rate model R0 is equal to R naught. Volatility model W0 is equal to V naught. Initial conditions are very natural in simulation and risk management. For example, in war simulation, you need today's portfolio value before you can simulate your tomorrow's losses. So we need W0 is equal to W naught. Without W naught, the future wealth distribution cannot be built. We have a risk management function. Risk task is war. Starting condition needed is current portfolio value. Risk task is expected shortfall. Starting condition, current exposure and position. Risk task is test testing. Starting condition is current balance sheet. Risk task is XVA, exposure simulation. Starting condition is current market state. Risk task is asset liability management modeling. Starting condition is your current yield curve and short rate. So initial condition is kind of the anchor point, right? It specifies the state of the system and the initial value. Essential for time-dependent PDEs. Commonly used in option pricing, portfolio value evaluation, and risk factor dynamics. Mathematically, this is the equation. Financial interpretation, known asset price today, known option value or portfolio value at evolution time, starting point for future evolution. Without an initial condition, the PDE cannot be solved uniquely in time. Okay, so that is what we have. And then we get into the next slide, basically types of initial conditions, starting value in the financial model. We have initial value condition, starting value, u x comma naught is equal to fx. This means at time 0, the function value is known for each state x. For option pricing, the slide kind of writes vs comma 0 is equal to v naught s. Now says v of s at time 0 equals v naught of s. Here s equal to current asset price, v naught s is equal to option value today as a function of s. In practice, today the option value may be observed from market price or computed from a pricing model. Then we have multivariable initial conditions. Slide gives us u of x comma y is equal to 0, g x y. Now say u of x comma y at time 0 equals g of x comma y. This applies when the model has more than one state variable. Example, stochastic volatility model. S0 is equal to S naught, V0 is equal to V naught. The noun says S at 0 equals S naught and V at 0 equals V naught, meaning variable S naught is equal to starting asset price, V naught is equal to starting variance of volatility level. This matters in models like your Heston, where option value depends on both asset price and variance. V is equal to S comma V comma T. The PD is now multidimensional in quant finance world. Model is black shows state variable ST, stochastic volatility S comma V comma T. Specific interest rate model R comma T, portfolio optimization W comma T, credit portfolio model, default density, time exposure. More variables usually mean a more realistic model, but also a harder PD, right? So initial value condition, starting value, this is this. Actual option pricing, V S naught, V naught S, where S is the current asset price, V naught S is the observed or computed option value. Time dependent initial condition, the more complex model, the initial state may depend on multiple variables. Example, stochastic volatility model for asset price ST and volatility S naught is equal to S naught 0 equal to S naught, V 0 equal to V naught. So that is what we get, right? Again, more variables usually mean a more realistic model, but also a harder PD. Then we get into the next slide, which is why these conditions matter in your quant finance. See, the slide basically summarizes the economic role of boundary and initial condition, right? They kind of encode that if your financial feature is like option expiration payoff, mathematical condition is terminal condition. If your financial feature is asset price limit, mathematical condition is boundary limit or boundary condition. If your financial feature is starting wealth, mathematical condition is initial condition. If your financial feature is interest rate behavior, mathematical condition is initial boundary condition. If your financial feature is early exercise, mathematical condition is free boundary condition. The key phrase is boundary initial condition translate financial contract feature into mathematical constraints. This is exactly how quant finance works. Derivative contracts say pay this amount if this event happens. The PD says given no arbitrage and market dynamics, but should that contract be worth today? The boundary initial conditions connect the legal or the economic contract to the mathematical model. Okay. So boundary and initial conditions are essential in PD model because they encode real world economic constraint, option expiration payoff, asset price limit, portfolio starting wealth, initial interest rate behavior boundary. Without this condition, pricing and optimization PD do not have economically meaningful or unique solution. The key idea is boundary initial condition translate financial contract feature into mathematical constraint to guide the PDE solution. Okay. Then we get into the next part, which is understanding your financial scenarios using your boundary condition, right? So again, the slide gives 4 key applications: European option pricing, American option pricing, portfolio optimization. See, when we have European option pricing, terminal condition is V S comma T is equal to max S minus K comma 0. This is a call payoff at valuation time. V S comma 0 is equal to current option price. The full pricing logic is that at time T, meaning payoff is known at 0, price today is unknown observed. Between 0 and T, PD connects the 2. In Black-Scholes, we solve backward from maturity today. Then we have American option pricing. The slide give you V S comma T max of V hold S comma T S minus K pronounced as V of S and T equals the minimum or the maximum of V hold of S and T and S minus K, meaning at each point in time the holder appears hold the option V hold S comma T or exercise immediately S minus K, right? So V S comma T is equal to max your hold value comma exercise value to create a free boundary problem. Why free boundary? Because the exercise boundary is not only advanced, the model must solve it. For American put, there is some critical stock price level below which exercise becomes optimal. That is a unique kind of distinction which we have in your American put. That boundary moves over time. Okay. Then we have portfolio optimization, initial wealth, W0 equal to W0, pronounced as W0 equals W0, meaning the investors start with known wealth W0. In portfolio optimization, PDE often comes from dynamic programming or the Hamilton-Jacobi-Bellman equation. The model asks you that given the starting wealth, today, how should I allocate between your risky asset and risky asset over time, right? And then we have interest rate model also, right? To be fair, interest rate model, the idea which we discuss. Okay, there's one more, like there is interest rate model also, right? Where initial short rate R0 is equal to R0, right? It is not given here, but please understand interest rate models are also one of the examples, right? Common application you can take. Okay, where R0, you are not, right? So R0 equals R0, this angle, the interest rate model for quant pricing, swaps, option caps, or in terms of the modeling, the model needs today starting short rate or yield curve. So that is what we need to understand. Okay, then we get into your summary. The important idea is the slide gives the key takeaways. Let's compress it into one clean framework. You have PDE, which is the rule of motion, initial condition, starting point, terminal condition, final payoff, boundary condition, edge behavior, free, boundary, unknown exercise, right? The most important point is the PDE gives many possible mathematical solutions. Conditions select the one solution that makes financial sense. This matters in pricing, hedging, risk, and optimization. Pricing, why PDE condition matter? Because it determines correct derivative value. Hedging is ensures delta gamma meaningful. Risk management prevents unrealistic exposure value. Portfolio optimization defines starting wealth and admissible strategies. Interest rate modeling anchor the curve and bond prices, right? So boundary initial conditions are fundamental components in solving differential PDEs, especially in quant finance. Why these matter? Because PDEs admit infinitely many solutions without constraint. Boundary initial condition ensures uniqueness of solution, economic and financial realism. Financial interpretation is boundary condition encode option payoff or expiration, early exercise features, American options, asset price and interest rate limits. Initial conditions specify your current asset price, portfolio starting wealth, and initial interest rate or world level. We have discussed all of these in the lecture, guys. Now, with that, we go to the practice question. We have European call terminal condition. Write the terminal boundary condition for a European call option. So if I have to do that, it is V S comma T is equal to max of your S minus K comma 0. This is very common, right? Let's say strike is 100, right? Then we say V equal to S comma T is equal to max of S minus 100 comma 0. The condition tells the PD at maturity, the call option is worth either stock price minus strike or 0. It's rule in PDE pricing and fixed maturity payoff. We know the final payoff exactly. Start the backward solution. Blackfield PDE solve from T to today. Ensure uniqueness. Without it, many prices could satisfy, or many prices could satisfy the PDE, right? Then we have boundary at S comma 0. So I have done this part both. Question number 2, boundary at S comma 0. State boundary condition for call option or asset price approaches 0. So that is for call option limit H tends to 0. S comma T is equal to 0. Right. Now say the limit as S approaches 0 of V of S and T equals 0. The financial intuition is if a stock price becomes 0, the call option has no useful upside as existed, especially for a non-dividend stock. The standard assumption, the right to buy versus asset at positive strike has no value. Okay, so that is the financial intuition. Then we go into question number 3, 4, 5, right? Question number 3, American boundary condition. Explain early exercise conditions and describe free boundary nature, right? For American call style payoff, right? So that is your V S comma T S minus K, right? Meaning the option value must be at least as large as the immediate exercise payoff. And you can also say V S comma T to the max of V PDE S comma T comma S minus K, meaning at each point choose a high value continue holding or exercise. Okay. This is a free boundary problem because the exercise boundary is known. This is the free boundary which we are discussing. Question number 4, portfolio initial condition. State initial condition for wealth process, that is V0, W0 is equal to V0, W0. meaning current wealth is unknown. This is essential because portfolio optimization asks start with this wealth, what strategy maximize expected utility or minimize the risk. Then we have interest rate initial condition also. Identify whether initial condition in identify required initial condition specific model, explain role in term structure modeling. In a short rate model, R0 is equal to R naught, right? Meaning today's short rate is known. In a style model, the starting rate is needed to generate the future distribution of interest rate and price bonds, right? That is what we need to understand, right? That's it, guys. If you go ahead, you will find the solution of each question. Question number 1, 2, 3, 4, 5. I have already explained you. You can go and see the detailed solution for better understanding, but I have already solved them in class, right? So I don't think there would be any problem to anybody of you, right? So, but do read the solution, right? Because they are explained in much more detail than what I've told you in class, right? So that gives you more idea of what we are trying to understand here. Okay, so this is what we need to understand very, very clearly, right? So first lecture of your PDE was all about understanding the initial condition, your boundary conditions, your starting value, your terminal value, and term structure connection, etc. Right? So the entire lecture is really teaching you one central quant finance idea that financial PDE plus your boundary initial condition is a unique financial solution. Or more practically, if you have PD component, let's say PD, financial interpretation is no arbitrage pricing or dynamic evolution. If your terminal payoff, it is a contract payoff, boundary condition, edge behavior of asset or rate, initial condition, current market state, PD component solution, financial interpretation is price, hedge, value, function, or risk measure. Where this appears in quant finance is that, such as your derivative pricing, Black-Scholes PD, for calls and put risk management, exposure in Greeks under boundary constraint, portfolio optimization, HGB PD, with starting wealth, interest rate modeling, bond price PD, exotic option, barrier, rebate, absorbing boundary condition, numerical method, finite difference, great need, boundary value. The clean takeaway is finance, the PD is not the whole model. The contract details, payoff, current market state, and economic state enter through boundary and initial condition. That is what turns mathematics into a usable pricing and risk management tool. Okay. That's it, guys. That's it for this chapter. I'll see you in the next chapter, but go back, revise it. I think if you revise it twice, you'll totally fine, right? So go back, revise it, guys. Once you've done it, you'll totally fine. Thank you.